The next part is opponent coordinate systems. Now we're getting closer into what we'll be using when we get into the lab. We use opponent type coordinate systems for describing color, and it really works better than any of the other systems, and we'll see why that is. So in 1976, a color space known as the CLAB system is the result of the mathematical transformation of the 1931 system. So in order to differentiate from other systems, particularly the Hunter system, all CIE parameters are marked with a star. Just a point of nomenclature and how things are identified. We see that the CLAB LAB numbers have this asterisk after them. And if you just see the numbers without the asterisk, technically that means Hunter lab. There's Hunter LAB system and there's CLAB LAB system. In common usage, most people refer to LAB in any form. We usually use the CIE system, and they most of the time forget to put the asterisks in there. I try to be consistent and put the asterisks in there, but I forget sometimes too because I just forget to put them in. Technically, if it has asterisks, it means the CLAB LAB. If it does not have asterisks, it means the Hunter Lab LAB. It's kind of a point of distinction between those two of them. But unfortunately, in common practice, it doesn't always work that way. Back when they were trying to make better color spaces, they wanted to find a color space which is uniform in terms of color difference. What we're talking about there is if you measure a distance between two color samples on the diagram, say you use a ruler to do that, and it has a certain color difference in terms of visual means that we see. What we'd like to say is if there was another, say, two sets of samples in a different part of the color diagram, if we measured that distance and the distance on the diagram in inches, say, was the same as the other pair of samples, the visual distance would be the same. So if it was a little bit off in the first set, it should be a little bit off in the second set, and the same amount off. So that's what they want to do to make it a uniform, linear diagram, so that the numbers that you get from the system, and difference numbers are what we're really interested in, the difference between the two of them, it should mean approximately the same thing visually. And they also wanted to develop a much simpler system to interpret, which made more sense intuitively. You could look at the numbers and get an idea of what we're talking about. So that was the object of this, what's really a mathematical transformation. To make it uniform and to make it easier to use and more pertinent to what it actually means as far as visually. The CLAB space, we again meet the three-dimensional coordinate system based on the theory of three opponent pairs of colors discussed previously. So when we talked about how we see color, if you remember the diagram that took the signals from the cones in our eyes, the red, green, and blue, kind of processed them together in our optic nerve system, and then that sent three signals to our brain. We have lightness and darkness, or white and black. We have a red-green scale, and then a blue-yellow scale, or a signal, however you want to discuss it. That is the basis for these LAB diagrams that we can use to describe color. L star means lightness, and we can use two different really systems on the same grid, LAB and LCH. L in both systems refers to lightness. A is the red-green axis, B is the blue-yellow axis, or we can say L is lightness, C is chroma, and H is hue. And we can superimpose those values or those numbers on our three-dimensional coordinate system. The following slide will show several depictions of the CLAB color space. So we can show it a couple different ways. This is probably the most typical way that we describe the LAB system, our opponent type coordinate system. It's similar to the chromaticity diagram in that we can think of, in this case, they're not horseshoe shaped, they're, in this depiction, square, although we'll see that's not quite right. We have planes And as you stack the planes on top of each other, the lower ones are darker colors, the higher ones are lighter colors. But in a particular plane, when we go on this axis or this axis, it means two different things. This axis goes from negative A to positive A. That's from green to red. So green is negative value for A, red is a positive value for A. In the B axis, blue is a negative B and yellow is a positive B. If we had a number that had a positive B value and a positive A value, what general color would that be? What hue of that color do you think it would be? It'd have to be positive B, so it'd have to be above this line going across, and it would have to be red, so it'd have to be this side of the B line, so it'd have to be in this quadrant for you mathematical aficionados. So what color would you say would be, if it was exactly the same of both, would be in that direction? What do you get when you mix yellow and red? Orange, right, orange. A positive B value and a positive A value would give you an orange, especially if they're both equal. So now when we have numbers, it can actually mean something to us color-wise. Make sense? Now that LAB could be the Hunter system, which is, we'll see in a little bit different than the CLAB system, but the concept is the same. Here's another way of looking at it. We have our hue circle that goes around here, starts at red, at positive A. We can also talk about that in terms of angles. You know how many degrees are in a circle, right? 360 degrees. If we go in this direction, we start here at red is a positive A, or we could say that's 0. That's what this H refers to as the hue angle. If we go up to here, that would be straight yellow, or excuse me, that would be straight yellow that way. That would be 90 degrees. Green would be 180 degrees. Blue would be 270, and then back to red at 0. So it's 360 degrees all the way around. By giving this small h value the hue angle, we can get an idea of what the color is. So if the color was, or the hue angle for a color was 45 degrees, what color would it be? Orange. Yeah, that would be right here, and that would be orange. If we had 180 degrees for the hue angle, that would be a green. So it's just another way of relating the colors in terms of a different number value. So that would represent the hue. The distance from the center point, and if we look at the center of our circle, that represents like the center point of the Munsell system, where they were all grays and whites and blacks, no color really, very little chroma or no chroma. That's the center point. The farther out we get from the center is our chroma value, so the more chromatic it is. So as you go out, it becomes more chromatic. Just like the Munsell system, very, very similar the way it's set up. And most of these systems, they're pretty much the same how they do things. There's just a few minor differences between them. If we pick a point anywhere on this plane, let's say, we can calculate what its A value and what its B value is. If we change planes, that's how we can find the L. Point right here, it would be a positive A value, and what about the B value? Be positive or negative? Negative, right? Because it's down below this line. Okay, and if that's the case, it would be blue and red and be kind of a purple color. So again, we can start to look at numbers and get some idea of colors by just looking at the numbers. Couldn't do that really with just our tri-stimulus values that we had before. Another diagram of the LAB system. And the center rod here are the white and black, gray axes. The farther you come out from the circle is chroma. And if you go around the circle, we have different hues, B-axis, and the axis goes like that. So just another picture representation of what we talked about. Here's another one, kind of a classic representation of the system where it's really a cylinder. Our center of the cylinder is our lightness value. The The farther out you get from that center is chroma, and as you go around the circle, you get different hues. Higher in the cylinder is lighter, lower in the cylinder is darker. Kind of shows these are the B axis, the A axes, and then the lightness axes, and where that cylinder falls in terms of hue, lightness, and chroma. We'll see mathematically there's two systems that can describe positions in a three-dimensional space. There's the rectangular coordinates, LAB would be, and the polar coordinates, which the LCH would be. Anybody remember that from math at all? There are some calculations associated with this, simple calculations. So these are the only things you'll have to calculate with these values. So when you calculate your LA and B values, what do you notice about the LA and B values? Where do they come from? You know, it's the only variables in here, which are the letters, are tristimulus values. So these values are calculated directly from tristimulus values. All the computers we have will do all these calculations for you, so you won't have to do these particular calculations. One thing about putting all these numbers into use practically is, nobody likes to do calculations very much. So that's where the computer systems that have evolved have really made these systems more practical, because the computer does all of these calculations for you. You don't have to worry about any of that. You measure your sample in, measure your standard into the spectrophotometer. The program that's in the computer calculates LAB values. And really what we're interested in when we do color values or color matching is delta values, or the difference in the LAB values from one sample to another. But this is how it's calculated. And this happens to be the numbers for the Hunter LAB system, which came first. These are the numbers for the CLAB system. You can see they both come from the X, Y, and Z values, but they have different ways of calculating. You can't equate the two of them, and there's no easy way to convert from one or the other. Like if you want to convert from Fahrenheit to centigrade, there's an equation that you can use and convert it. There's no simple equation that goes with these. They're either one system or the other. Again, they're all based on the tristimulus values or the X, Y, and Z values. That's where those absolute numbers come from. The absolute numbers for LA and B or LCH, and those can be calculated, and those are calculated by the computer. We're not necessarily interested when we're doing color match the absolute values. What we're interested in are these delta numbers. So we have a standard that our customer gave us that has its own LAB numbers, and then we try to match that. So we make up a formula, run in our injection molding machine, get a chip out, and then we get LAB numbers for that particular batch. What we're interested in is the difference between those two of them. So we take the L value from the batch, subtract the L value from the standard, and we get our delta L value. Same thing with the A and the B. And it's important that you do these calculations or the subtraction where you start with the batch and you subtract the standard away from it. Because one of the things that's important about these numbers is not only the size of them, but the sign, whether it's positive or negative, because that tells us which direction it's off, whether it's red or green, blue or yellow, that sort of thing. In terms of LCH, the calculations, basically the difference in chroma is the chroma of the batch minus the chroma of the standard, and this is the way that each chroma is calculated. We'll do this in a later class. And then the hue, you can't really just calculate it completely or directly, so what you have to do is take the total difference between all the different axes, which is delta E, subtract out the lightness difference, and subtract out the chroma difference, and whatever's left over is the hue difference. These are the numbers that are important, these delta numbers. This triangle there means delta or difference. It might be a D there, a small d, or a capital D. All those mean difference. There's two ways of calculating delta E. You can do it with either LAB numbers or LCH numbers. And the way it's calculated, if you remember from math math class. It's how you calculate basically the hypotenuse of a triangle. You take the, in this case, in 3 dimensions, square the L value, the A value, and the B value, these difference values, get that number, and then you take the square root of it. One of the reasons to square it is you get rid of the negative numbers. And the important thing with these numbers is what they mean to us in terms of color difference. If the delta L value is positive, it means that our sample is lighter than the standard. If the L value is negative, it means the sample is darker. Right. If the A value is positive, the sample is redder, or we could say less green. Both of those terms mean the same thing. And as we go through this in a little more detail, we'll explain why. One, it's better to say in one case it's the sample is redder, or in another case the sample is less green. If A is negative, then the sample is greener or less red. Technically the same thing. If the B value is positive, the sample is yellower or less blue. And if the B value is negative, then the sample is bluer or less yellow. So just by looking at the delta numbers from your standard and your sample, you can tell roughly how the differences of your two colors are. The number or the value for those delta numbers tells you how far off it is. So the bigger the number, the farther off it is. And the sign of the difference tells you which directions it's off, whether it's redder, greener, bluer, yellower, that sort of thing. And then color difference numbers can be depicted graphically. And then the next exercise will show some of those things. So we can have numbers to describe the difference, or we can use graphs. The 2 dots there represent 2 colors, and the total delta difference, or the total color difference, is delta E. And you can draw a line from one to the other and measure that line. That would tell you what the total color difference is between those 2 colors. It doesn't break it into the individual components. We can have 2 samples here and look at them on a graph, and we can see, say this is our standard up here, the top one. The bottom one is our trial. So what can you say about the differences between those? Now compare your trial to the standard. What is it in terms of redness? Is the trial redder, or redder than the sample, or less red than the sample? Red is, remember, in this direction. So which has a greater number on this graph going to the right? The standard or the trial? Standard has a bigger number, so that means the trial is less red than the standard. Okay. What about in terms of blue? Is it bluer or not as blue as the standard? Bluer, much bluer, because it's towards the bluer end. Lightness we can't tell from this. What about the chroma? Is it a higher chroma or a lower chroma than our standard? And that would be the distance from the center to the sample. So if we measure the distance there with the standard and the sample trial, which one is farther away from the center? The sample, right? It's on the outside of the circle versus the inside of the circle. So that means the trial has a higher chroma than the standard. And you can tell all that by just looking at that graphic representation. Or if you had the actual numbers, you could tell the same thing. It's 2 ways of describing the same difference. And here we have where these 2 samples fall in absolute LAB space. We have our standard in the center there of this crosshairs, and our sample is there. And that's how, when we look at it on our spectrophotometers on our screens, and we have a plot of it, this is the way it looks. It always puts the standard in the center of our plot, and then our sample falls somewhere other than the center. Okay? By looking at that, what can we say about our sample versus our standard in terms of red, blue, green, yellow? More yellow, right? And and a little bit red. Comparatively, that's more off in the yellow direction than in the red direction, right? Because it's farther this way than it is that way. So that's what we can tell by looking at our screens on our spectrophotometer. Here's just another picture of the same thing. And in this case, they're using less bluish and more bluish, more reddish and less reddish. What we say is, in this case, whether it's less blue or more yellow kind of depends on what color it is. If we were working with like an orange, and that's what we got from our screen, then we would say that it's not yellow enough because it needs more yellow. We wouldn't talk about an orange in terms of blue, not enough blue or too much blue, because it really doesn't make much sense. We use the term yellow, either more or less yellow, or in this case, too yellow. If we were using or working with a green, for instance, and it said it was too red, well, that doesn't make much sense to say a green is too red. What you would say in that case is you would say it's not green enough. It doesn't have enough green. Even though saying too red technically is the same thing. But just in everyday usage and making sense, in that case, if we were working with a green, we'd say it's not green enough versus saying it's too red.